In this video, we're going to be talking about electromagnetic waves. So electromagnetic waves are basically two transverse waves that are perpendicular to each other. So we can see that in this image over here. They both intersect and go like this. So because they go like in a perpendicular way, they're perpendicular to each other. Now, electromagnetic waves have an electric field and a magnetic field. Electromagnetic waves do not require a medium to transfer energy, and they can travel through space. Their speed in a vacuum, which is in space, would be around 300 million meters a second, or 3 times 10 to the power of 8. Let's talk about electromagnetic waves for a second. People knew that we have electric waves, over here. People knew that we had electric waves and we had magnetic waves. People, when they were experimenting with these electric fields and magnetic fields, they noticed that when an electric field started changing, the magnetic field started changing. And when the magnetic field started changing, the electric field started changing. So by noticing this change over here, or when scientists observed this, they noticed that it went in kind of a up and down motion, and it could act independently. Basically what happened is when the electric field changed, the magnetic field changed. If the magnetic field changed, the electric field changed, and this kind of created a chain reaction of complete changing fields. And because of that, it created an infinite loop where these fields would continue to change forever and ever. This kind of created this up and down motion that we see in regular waves today. So this wave is not exactly the best representation. However, this wave is. So the electric field will be represented in the y-axis, the magnetic field in the z-axis, and this direction, or this velocity where it's going through this direction, is in the x-axis. Now this x, y, z-axis is typically measured in the 3D coordinate graph. So I'm gonna draw that real quick. We have the electric field over here. We have the velocity, or the direction it's moving in. And lastly, we have the magnetic field over here. That's kind of how it's being represented in this wave over here. And the thing about electromagnetic waves is it comes from the name itself. Electro, coming from electric field, magnetic, coming from magnetic field, and this creates a type of wave over here. Now this wave is able to move through space. For the Earth, the main source where we get most of our electromagnetic waves comes from the sun, over here. The sun sends light waves and other kinds of waves towards the Earth. We also have some technological instruments that are also able to manipulate the waves and create newer waves, or new different types of waves. For example, X-ray waves and radio waves. So if you look at a magnetic field, magnets can exert force on them exert force on objects without touching them. So anything between this magnetic field is able to exert the force on and is able to come towards the poles over here. For the electric field, what's happening is if it's a positively charged particle, then what happens is that it's able to exert force. If it's a negatively charged, then it takes in that force. Now here's the thing, based on that particle that's happening, so I'm gonna draw the particle over here. So let's say this is the particle right here. If the particle's vibration with the electric and magnetic field is moving at a rapid rate, or it's vibrating a lot, then what happens is that it starts to basically, its frequency is going to be very high because it's vibrating or moving up and down a lot. So, and the particle will be located over here. It's driving the entire wave. So here in this situation, the frequency wouldn't be that much. But here in this situation, the frequency would be a lot. And that's what we can differentiate between the different types of waves in the electromagnetic spectrum. If you look at the electromagnetic spectrum, we can tell that the wavelength over here, the wavelength is the distance between crest to crest and trough to trough. We can tell that the difference between the wavelength is different over here compared to over here where it's very stacked. So let's take radio waves, for example. Radio waves is the longest. It is the longest wavelength, but has the least frequency. Now, in the electromagnetic spectrum, what happens is wavelength and frequency work inversely. So if the frequency is high, the wavelength's low. If the wavelength's high, the frequency is low. So in this situation, radio waves have the wavelength's high, but the frequency is low. If we were to look over here with the radio waves, that particle that's driving it, it doesn't have that much energy or that much electrical, it doesn't have that big of an electrical field or magnetic field, and because of that, it's not able to exert a lot of force, and hence it's going to be it's going to have very long wavelengths that we know. However, if we were to look at X-rays or gamma rays, it would have a very high frequency because the particle's exerting much more force and much more energy, so it's going to be going faster and faster and faster. Keep in mind, these are transverse waves and these aren't the best drawings. However, this would be the best drawing because it shows the magnetic field, the electrical field, and the way or the direction it's moving through. Electromagnetic waves are everywhere. So they can be found in multiple objects, like for example, the sun allows visible light, X-rays, like X-ray machines create X-rays, radios have radios, microwaves create microwaves, infrared rays like the sun also fires and radiators create this. Visible light is basically what our eyes see. So our eyes are not able to see all of this, they're only able to see one basically, which is visible light. Now, the thing with visible light is when it goes through a transparent object, it's able to split into multiple colors instead of just being the white light that the sun emits. Let's take the sun for example. Let's say that sun gets the visible light or whatever that light is, and that electromagnetic wave lands on a leaf. Now, if it lands on a leaf, once that wave hits it, it interacts with the chloroplast molecules. And those chloroplast molecules that we understood from waves, they can either get absorbed, reflected, or refracted. In this situation, the chloroplast is refracting green. So that gives us the illusion that the leaf is green. When a electromagnetic wave, interacts with an object or molecule, it can either get reflected, refracted, transmitted, or absorbed. So reflected means it gets out, so what we see. Refracted means it changes direction. Absorbed means it gets absorbed by the object and the wave doesn't continue any longer. And then we have transmitted, where it goes right through. These waves travel at the speed of light, and keep in mind that speed in a vacuum would be around 3 times 10 to the power of 8 meters per second, or 300 million meters per second. Let's do a small demo. I'm going to have 2 phones over here. The phones, they also emit waves, but we're not able to see those waves because our eyes are not able to pick up on those waves. However, there are waves all over this room and probably all over around you. So let's do a simple experiment. So I'm going to call on this phone to this phone over here, and I'm going to do it regularly, okay? So we're getting the call, as you can see over here. So now what I'm going to do is I'm going to wrap this phone around aluminum foil. Alright, so now let's try it again, this time with aluminum foil wrapping. As you can see, it's not able to pick up any of the device.
Please leave your message for 9.
So because we're blocking the signals to entering into the phone, it's not able to pick it up. Hence, it's saying it's not able to find the number. In this situation, that proves how electromagnetic waves are being used in day-to-day life.